You ever stop and wonder what makes a remote control work? Or a microwave? Or even one of those old-school video game consoles? Well, chances are it's a tiny computer brain kind of like this one, the 8051 microcontroller. Seriously, this thing is one of the most fundamental, most influential pieces of tech ever made, and it's hidden inside countless gadgets we use every day. So let's get into it and see how this tiny brain actually works.
And here it is. Yeah, it looks like a small black rectangle with a bunch of metal legs, kind of like an insect, right? But don't let its looks fool you. This single chip is a complete self-contained computer. I'm talking a processor, memory, and ways to talk to the outside world, all packed right into this little guy. For decades, this wasn't just a computer brain. It was the brain behind a whole revolution in electronics.
But how does it do all that? How can something so small be so powerful? What's actually happening inside this little black box and through all of those pins?
To figure that out, we're going to take a guided tour of the 8051, starting from the outside and working our way in. We'll check out how it connects to the world, how it thinks, and even how it remembers.
Okay, first, and this is the most important part, this isn't just a processor. A microcontroller, or an MCU, is an entire computer system on one single chip. It's got the central processing unit, the CPU, which is the core that runs all the programs. But it also has its own memory for storing those programs and data, and all the input-output, or I/O, it needs to interact with stuff like buttons and screens, the whole shebang.
All right, so our tour is going to start on the outside with the only way the 8051 can sense and affect the world around it, through its pins.
And this diagram right here, that's our map. Think of it like a floor plan. Every single signal, every bit of data, every command, it all has to go in or come out through one of these 40 connections. That's it.
Now, 40 pins can seem like a lot, but to make sense of it all, we can group them up by what they do. You've got the absolute essentials, like power. You've got the oscillator, which is basically the chip's pulse. Then there are some control signals for managing things, and, most importantly, you've got the I/O ports, which are the real workhorses here.
So let's start with the absolute basics. Just like any electronic device, the 8051 needs power to even wake up. That juice comes from a positive 5-volt supply connected to pin 40, you see it labeled VCC, and a connection to ground on pin 20. Simple as that. Without these two, nothing else happens. It's a paperweight.
Next up is the heartbeat. See, a computer needs a steady clock pulse to execute instructions one by one. The 8085 gets its rhythm from an external crystal oscillator that you hook up to pins 18 and 19. This clock signal is what dictates how fast the chip runs, and it synchronizes every single operation it performs.
Okay, now we're getting to the really fun part, the I/O ports. These are the chip's senses and its voice. An I/O port is really just a bundle of pins, usually 8 of them, that you can program to either read an input, like, say, the press of a button, or send an output, like turning on an LED.
And the 8051 comes loaded with 4 of these 8-bit ports. They have these really creative names: port 0, port 1, port 2, and port 3. That gives us a grand total of 32 individual I/O lines that we can use to connect to whatever we want in the outside world.
But here's where it gets clever. There's a little twist. While port 1 is pretty much a dedicated I/O port, most of the other pins are hiding a second identity. They have these alternate functions that are absolutely critical for unlocking the 8051's full power. And we'll get back to that secret in a little bit.
Okay, let's move our tour from the outside connections to the inside and see how the 8051 stores information. A good way to think about its memory is like it has 2 main areas, a library for all the permanent instructions and a workbench for all the temporary data.
So the library, that's the program memory, or ROM. This is where the main program, the big set of instructions, is stored permanently. You can't change it while it's running, so it's read-only, kind of like an instruction manual. The workbench is the data memory, or RAM. This is just a temporary scratch pad where the chip can store variables and do its calculations while it's running. You can read from it and write to it all day long.
Now, what's really cool here is how the 8051 keeps these 2 types of memory totally separate. It has a dedicated space for program code and a completely different space for data. This is a classic computer architecture design, and it also means that both of them can be expanded with external chips if the memory inside isn't enough.
Let's zoom in on that internal RAM, that scratch pad. It's not just one big, messy pile of memory. Oh no, it is meticulously organized. At the very bottom, you have these things called register banks for super fast calculations. Then above that, there's a block of memory where you can flip individual bits on and off, which is incredibly useful. And then at the top, you have a very special area.
And that very special area is what we're looking at next. This section of RAM is basically the chip's control panel. This is how a programmer actually tells all the different hardware components inside the 8051 what they're supposed to be doing.
These are called the Special Function Registers, or SFRs. The best way to think of them is like a bank of switches, dials, and status lights. You want to configure a timer? You just write a value to the timer's SFR. You want to see what's happening on an I/O port? You just read its SFR. They are the direct line to the hardware.
A perfect example of an SFR is something called the Program Status Word, or PSW. This one single byte acts like a dashboard for the CPU. Each bit inside the PSW is a little flag or an indicator light that tells you exactly what happened after the last thing the CPU did.
So what are these dashboard lights telling us? Well, the carry flag, or CY, it'll light up if an addition resulted in a number that was too big to fit in one byte. The register bank select bits, they let you quickly switch between different sets of working registers. The overflow flag warns you about errors in certain kinds of math. And the parity flag even tells you if your result has an even or odd number of ones. Super specific, but super useful.
All right, now for our final stop. We've seen the external pins and we've peeked at the internal memory and controls. So let's connect those two ideas together and see how the 8051 can grow beyond its own on-chip limits.
So the standard 8051 comes with 4 kilobytes of internal program memory. I mean, that's a decent amount, especially for the time. But what if your program is bigger? What if you need more space?
And this brings us back to the secret of those dual-purpose pins. This is their moment to shine. When the 8051 needs external memory, port 0 completely transforms. It stops being a simple I/O port and becomes a shared highway, a bus, for both data and memory addresses. At the same time, port 2 pitches in to provide even more address lines. And together, they let the 8051 break out of its tiny shell and talk to up to 64 kilobytes of external memory. It was just a brilliant piece of engineering, a super clever way to add huge functionality without adding more physical pins, which were a big deal for cost and design back then.
So when you look at it, the 8051 isn't just a simple chip. It's an entire ecosystem with its own memory, its own controls, and this really clever way to expand its reach. And this fundamental design, a complete computer on a single chip, is really the ancestor of the tiny brains that are powering countless devices today. Which kind of makes you wonder, what tiny brains are powering the world around you right now?